Okay, so my mentor was Nikhil M., a current PhD candidate at Stanford University, and I'm currently presenting from Cupertino, California, and I'm a junior at Monte Vista High School. So for what motivated me to choose this topic, I'm a classical musician. I play the classical guitar, and I'm currently attending the San Francisco Conservatory of Music pre-college program. And I've always wondered what made a certain piece like sound like it was from a composer. Like for example, if I heard a Bach piece, I'm usually able to recognize that it's Bach, but I was never really sure why that was. So I combined my interest in both music and neural networks and tried to find a solution for this problem. So my research objective for this was to create a predictive model that could accurately identify the composer of a classical piece of music based on the extracted audio features. So by harnessing capabilities of artificial neural networks, I aim to engineer features that could capture the distinctive elements and nuances of different composer styles. And then these features would serve as the foundation for the training and evaluation of the model. So what made this so difficult was that classical music pieces every composer has their own unique style, but on upon that, unlike genres such as pop or rock, where it's often easy to figure out what a certain composer or artist style is, classical music spans such a large time period, and composers are always innovating, so it's very hard to figure out certain tendencies that composers have, and then this makes it very hard to find meaningful patterns and features within their music. So to do this, I had to prepare a data set. So this data set included 2,000 Western classical tracks from Audio Sets Erlangen. And the audio labs were founded in 2010, and they were unique worldwide in their mission and international approach. So it consists of a team of globally renowned scientists who are working to shape the future of audio and multimedia technologies and research. So they have a lot of public data sets, including audio features that they allow people to use to train models. So this data set had a wide range of composers and musical styles, covering from areas from the Baroque period, which is the 17th century, to the modern era, which is the 21st century. And each track in the data set had a corresponding composer. And then for this current data model, I used a training set of 80% and a testing set of 20%. So I had to modify the data. So as you see in the image below, I modified it such that I only include the first 20 seconds from each piece, and then I incremented it by 0.1 seconds, and then I split each chord into three parts. So in the original data set, it just had a chord and then the duration. So if we look at the image below, we see the original chord here was a A major minor seventh chord. So I one hot encoded this so that it could be put into my LSTM model. So as we see below, under the letter A, there's a one, and then the rest of the letters have a zero, indicating that it's not that letter. And then the same thing goes on for the triads and the sevenths. So for the model architecture, I used a LSTM, which is a long short-term memory model. And LSTMs are a type of recurring neural network that is specifically designed to model sequential data, and they excel at capturing long-term dependencies and patterns in time series data, which makes them very well suited for analyzing music. So the LSTM layer units, it maintains an internal memory state, which allows the model to retain relevant information over extended time intervals. And this memory mechanism is what enables the model to capture the complex patterns that are present in classical music compositions. The output of this LSTM is then passed through a dense layer, which is known as the classifier. And then the dense layer maps these learned representations from the LSTM to the predicted composer. So the activation function used in the dense layer depends on the specific requirements of each problem. So for this, I used a softmax activation, which transforms the output from the previous layer into a probability distribution because I felt that would be the best way to represent my results. So as we see the equation below, Zi is the input score for the class and K is the total number of classes. So in this equation, the numerator is that it computes the exponential for the input score, ensuring that the value is positive, and then the denominator calculates the sum for all the classes. And then this normalization term helps ensure that the output probability sum up to 1. And then by dividing the exponential score by each class, the softmax actually guarantees that the resulting value represents valid probabilities. And then in this situation, a higher score would correspond to a higher softmax. Next, the training and evaluation. So the training process involved presenting batches of data as training examples and updating the weights based on the computed gradients. So I used a batch size of 12. And then this helps identify the underlying patterns and relationships in the data, making accurate features. The model provided a list of predicted composers for each piece, as well as their respective probabilities, and the top 3 predicted composers and their probabilities were reported for each piece. This model predicts the composers for the test examples based on the extracted features, and then those predictions are compared against the ground truth composer labels to calculate various evaluation metrics, such as the accuracy and the precision. Now going over the results. So the training model was evaluated on separate testing data to assess its predictive performances, and it had an accuracy of 50.4%. But despite the model accuracy, the model demonstrated encouraging indications of its capability to identify the composer of the given piece. Notably, the true composer was in the top 3 composers in over half of the cases. But if we take a closer look specifically at the table on the bottom right, we can see 2 outliers, namely composers 1 and 7, which had a lower performance in the top 3, achieving 40% inclusion and only 10% in the top prediction. Further investigation revealed that both of these composers were often predicted as composer 12, with the latter being included in the top 3 predictions 90 and 100% of the time, respectively, and selected as the top composer in 60 to 40% of the instances. This suggests that there's either a similarity between these two, but what is more likely is the actual lack of data which was available for composers 1 and 7, with each only having 10 pieces inputted into the model. If we exclude composers 1 and 7, the model actually demonstrates very good accuracy of predicting the correct composer with a top 3 prediction rate of 82% and a top composer prediction rate of 46%. So what are the impacts of this? This evaluation shows us how the model's ability to accurately predict classical composers based on audio features and demonstrates promising generalization capabilities across different compositions and composers. And this indicates that it has the potential to capture the distinctive elements of each composer style effectively. This suggests that this method could be really influential and relevant in either different music types or even multiple different sources around the world, and shows that machine learning models can serve as tools to assist and augment human understanding rather than replace it entirely. I think that by leveraging advanced techniques and comprehensive data sets, the machine learning can play a crucial role in the appreciation of and analysis of both classical and other forms of music. And I feel like one way that this model could have been made better was the lack of data, especially as shown in the composers 1 and 7, could have made the model more accurate and provided more insight. That's it. Thank you for listening.
Cool. Nice work. I, for one, have a few questions before we jump into one of the Q&A questions. Can you take me back to your one-hot encoding slide?
Yeah.
So you said one-hot encoding, and I especially am guilty in the data world of using a term, explaining the term, but not really explaining why we used it. So I wanted to double click into, you mentioned you one-hot encoded, totally on board with it. What is one-hot encoding, just as a reminder for the speakers in the audience, and then why did you do it?
So one-hot encoding, as you can see in the image below, I've associated either a 0 or 1 in each category. So it's basically taking certain data and putting it as 0 as 1. And in my instance, I had 1 as true and 0 as false. So for the letter category, 1 would mean under the A, it's 1. So that means that's true. And then for the rest, it's 0, meaning that's false. And the reason I did this was because the LSTM, the original data set, as shown in the bullet point, was just A underscore major underscore minor 7th. And even though that's like relatively easy for us as humans to understand, the LSTM model can't actually gain anything from just these set of letters. So by one-hot encoding it, we're actually able to input this data into the LSTM.
Exactly. Yeah, exactly. Right. So, so what one-hot encoding allows us to do is tell the model at every time interval what does and does not exist in the, like string that originally existed in the data, right? So A major minor 7 has no minor B chord, right? The letter underscore capital B, lowercase b. And that's what we're showing here. And then I had one more. Oh, can you take me to your predictions?
Yeah.
So I also noticed a couple of outliers that were overperformant in their accuracy for top composers. You mentioned 1 and 7 being underperformers and commented on them, but I saw composer 3, I saw composer 6, and I saw composer 11, all of which having a 70% or greater top composer prediction score. Did you do any analysis on who those composers are and potentially why those scores are higher?
So I didn't actually want to, because due to like my background in classical music, I knew that like how certain composers had similar styles. So that's why I actually used the composer instead of using the actual name of the composer, I replaced it with numbers so I could remove all bias from the study. But for your other question, like for composer 3, it has like one of the largest it has the largest like available data set. So I feel like that's the reason why it had such a high like accuracy. But for composers, I think 6 and 11, as you noted as well, they also have only 10 pieces. So I feel like this also contributed to the really high score where the model wasn't able to get like a full understanding, and the pieces that were provided might have been like very similar or like from the same suite or something, and that's why it was able to have such a high predictability rate.
Totally. Just an alternate perspective on it as well. Maybe, and you know the data better than I do, so I'm not suggesting this is the case, but an alternative explanation could be that maybe there is enough signal in those 10 samples, and that composer is just that unique compared to all the other composers studied. Just a completely different style, right? Wildly different, and so easily detectable with a lower sample size compared to the rest. Not saying
Yeah.
that's the case, but it could be.
Mhm.
Cool. We have a couple of questions in the Q&A as well. So based off of your discoveries, do you think there's a genre of music that would be even more difficult to predict than classical music?
Uh, I don't think there is, because I mean the term classical music, especially like in the way I use it here, is such a broad term that spans across so many centuries from the 17th to like the 21st century. And like if we think of something else, like for example, pop music or something like that, it's traditionally considered a bit more simplistic and it's obviously more modern, but it's just such a shorter time frame, and the amount of actual complexities within each piece in general. Obviously, there's some like songs which are like extremely complex and have a lot of diversity, but especially due to the shorter time frame and the lack of like diversity in the subject, I feel like it would be easier.
Cool. And the second question, how did the hidden layer detect the patterns and match with each composer's style, since the pattern emerges sometimes over many seconds of audio or even after a couple of minutes, and this varies between composers?
So from my understanding, the hidden layer, it uses engineered features, so I don't actually know like what it's taking into consideration when it makes these judgments. But I think the point about certain composers, like the patterns going over many seconds or even couple of minutes, because I mean some of these pieces are like 30 plus minutes. So I feel like one way the model accuracy could be further improved is I only use the first 20 seconds with 0.1 second intervals. So I feel like extending that to the whole length of the piece would be a lot more influential and provide deeper understanding.
And also, I think your model choice hits on this as well, right? The choice of a long-term, short-term model bakes into your prediction set a model that also has like more extensive knowledge over the data it's modeling. It's not necessarily just predicting at a specific time interval what composer it is. It's actually looking back into the past and
Yeah.
saying, all right, with this and into the past couple of seconds, what composer do we think this is?
Yeah.
Awesome. Awesome. Great job.